This is really just a summary video that goes over a lot of the models that we've seen so far. And I want to begin with one of the very first models we saw, where we compared or tried to estimate the proportion of people in the population that were right-handed. And so what we have here is the flow chart, and there's the likelihood function. And I should note that in this video there's going to be color coding with likelihoods, priors, hyperpriors, and hyperpriors identified by these colors. So at the bottom we've got our likelihood function, and the ones and zeros, one for right-handed, 0 from left-handed, are assumed to come from our Bernoulli distribution with some parameter theta. And we said that our prior for theta was going to be a beta distribution with these parameters, and right there is that beta distribution with these parameters. Right here we have Bayes' theorem. And remember, the problem with Bayes' theorem is that it's very difficult to calculate the probability of the data. So because it's a constant, we can get rid of it and change the equal sign to a proportionality sign, which gives us this. And now that we've got this, we can implement it. And we can implement it because we know what the probability of theta is. There's the prior right there. And we can calculate the likelihood, the probability of the data given theta. So remember, what a likelihood function does is it keeps the data constant. And in this case, we had z equals 9 right-handed people in n equals 10 trials. So if we keep that constant, we can calculate the probability of getting any number of values of right-handed people is going to be theta to the z, 1 minus theta to the n minus z. These things are constant. And so what we can do is we can arrive at our posterior distribution by theta by going on a random walk. And the way our random walk worked was we'd have theta proposed, and that would be equal to theta current plus delta theta. So we go through this random walk having all sorts of currents and proposed, and then we choose between them, and we would accumulate values of theta current. And again, that would be easy to do because we know this thing here, there's the prior, and we know this thing here, that's given this, so we can calculate theta proposed and theta current 10,000 times, and the final accumulation of those 10,000 theta currents would be the posterior distribution. Now we're going to move on to a hierarchical distribution. Very simple example with one mint and one coin. Again, the ones and zeros arise from a Bernoulli distribution with some parameter theta. But whereas up here, where we attach numbers to the prior, well, here we're going to set, to make things simple, we're going to use omega kappa parameterization. We're going to set kappa to be equal to 100, but we're just going to name omega, and we're going to let JAGS determine the posterior distribution of omega. This is our prior, and here in blue we have hyperprior, which is relatively flat. If we think about this in terms of Bayes' theorem, here we have Bayes' theorem. The only difference from what we saw before is now we've got a joint distribution instead of a single distribution. Again, the data is constant. Change that to a proportional sign, that gives us this. To go from this line to this line, a couple things happen. First is we take our joint distribution and we factor it out. We factor it out into our hyperprior, which is the probability of omega, and then the prior, which is the conditional distribution of theta given omega, and there we have our likelihood function. The other thing that's happening is that when we think about our likelihood function, we decide that once we know theta, we no longer need to worry about omega. So we factor this thing out into likelihood, prior, and hyperprior. Now, this isn't particularly realistic because we've got one mint and one coin. So now we make something more realistic with 28 therapists. Again, at the bottom, our likelihood function, ones and zeros, depending on whether or not the therapist could correctly identify the hand. But now in terms of our prior, we've named both kappa and omega, and we're going to let JAGS determine the posterior distribution of it. Here's our hyperprior, and we specify those both for omega and for kappa. I haven't gone into details here, but remember, to get from here to here, there is that stuff about kappa minus 2 plus 2 business that we have to do to account for this. But in any event, in a study like this, there's really two things that we're interested in. One is this theta for each one of the therapists. And notice that we've indexed theta by therapist because we're going to potentially have different thetas for the different therapists, and that makes us have to use this double square bracket nested indexing for theta therapist. The other thing that we're really interested in is this value of omega, because omega reflects the overall ability of a therapist to detect a hand, because these individual therapist values were deemed to assumed to have come from this distribution with some modal value omega. We made things even more complicated here in batting, in that now we've added a new layer. So at the bottom we've got our likelihood function. We've got the number of hits for each individual player is deemed to arise from now a binomial distribution with some sort of theta, which is specific for the player. So we're going to have 948 values of theta player. And the prior for those is listed right here. And the prior is a beta distribution with omega, but omega is indexed by position. So now we've got omega indexed by position. We've got 9 of these that reflects the overall ability of a player at a particular position to hit the ball. And then we've got our hyperpriors here. So the hyperprior for omega is also a d-beta distribution, but it's going to have values, parameters of omega 0 shown here. And what those represent are the overall ability of a baseball player to hit the ball. So we've got overall ability of a baseball player to hit the ball, the ability of a player at any particular position to hit the ball, and the individual player's ability to hit the ball. And because we've got a prior and a hyperprior, these things we can refer to as hyperpriors. Now we move on to the wing length example, and we're trying to determine whether there's a difference between male and female falcon wing lengths, and also look at the different variabilities, because we're going to assume they don't have the same variability. Now, instead of having a binary dependent variable, we've got a continuous variable, which is wing length. And those wing lengths are going to have as our likelihood function. And this is a much simpler example in the sense that we're no longer hierarchical. All we've got is a likelihood function and its prior. But in the likelihood function, we're going to think of those wing lengths as arising from a normal distribution with some expected value shown here and some variability shown here. Now, we went over when we were in week 3, how we deem values to arise when we're thinking about a general linearized model or in Bayesian data analysis. We're going to assume that individual observations, so if we're thinking about this likelihood function and how it works, we're going to think that individual observations are going to arise from a normal distribution with some sort of a mean, some sort of an expected value, and some sort of a parameter indicating variability. So there's the expected value, and there's the parameter that captures variability. What makes this a little bit nasty is that the formula for the expected value of wing length for any individual bird is given here. We're trying to determine wing lengths for the different species, or different males and female sexes. So we've got this double bracket nested indexing for sex here, also for sex here. We call that in a normal distribution. In the case of JAGs, we parameterize by tau instead of sigma. And then finally, we come back to what we just did in this week, the bugs and birds. We return to binary dependent variables, and here we're going to have 2 of them, 1s and 0s for breeding, 1s and 0s for survival. Now, very much akin to what happened up here, we're going to have a rather complicated function for our parameter. Now, the parameter in this case is going to be the theta parameter of a Bernoulli distribution. And it's going to have this it's going to be calculated through this rather nasty looking function. So what we're going to do operationally, we're going to get the logit of theta using this nasty function, and then we're going to use this trick, e to the fx, or 1 plus e to the fx, to return us to theta, which is what we're really interested in. So that's how we're going to get these thetas. That's our likelihood function. And we're going to get 845 thetas for theta for breeding, theta for survival. Now we have to establish the prior for those. Well, we're going to very simply specify these guys that are in black, these 3 here, and these 1, 2, 3, 4 here. For example, we could specify a phi as being a normal distribution, mean 0, a relatively flat with a very low level of precision. In terms of the prior, these guys are different. Alpha phi and alpha beta are going to be different because their prior is going to be a multivariate normal distribution that's going to have these 2 parameters, mu and sigma. So there is mu and there's sigma. Perhaps the best way to think about these alpha and betas is that alpha beta is breeding ability, alpha phi is survival ability, in much the same way that in our batting example, we had players' batting ability. The priors for alpha beta and alpha phi are shown numerically here. They're shown graphically here. So this would be the prior. So we've got some sort of a mean for survival, a mean for breeding. That's captured by this vector. And then the association between the two is captured by this vector. And of course, we're going to have to specify our hyperpriors for these parameters. So we're going to need to have hyperpriors for alpha phi and alpha beta, also for the standard deviation of breeding, standard deviations for survival, and most importantly of all, as you saw in the previous illustration, what we're really concerned with is rho, the correlation between breeding ability and survival ability. In any event, this has just been an overview of some of the models we've seen to date, and the whole point is that by using Bayesian data analysis, we've got a lot of power and a lot of flexibility to address some of the complicated issues that we see in environmental sciences.